We will start with the simple nested loops join algorithm, which is pretty much the simplest algorithm you can imagine. There's a note here on the right for simplicity. In particular, we are not going to present an iterator-based implementation for these join algorithms, as it does complicate the discussion a bit to think about how to implement these as an iterator. So we will just for now show them as a standalone algorithm. We will assume that the data streams out of them, so we are not going to account for the cost of writing and output, because eventually we want these implemented as iterators that pass the outputs back through the next function. So in the simple nested loops join, for each record little r in table R, and for each record little s in table S, if the theta predicates of R holds for little r and little s, then we will add the pair r comma s to the output. You can see a picture of this on the left, where we have the r tuples laid out on the y-axis of a Cartesian plane and the s tuples laid out on the x-axis. The join is navigating the cross product of these two tables, so that's the Cartesian plane. So how does it navigate the cross product? Well, for each record of R, we scan through all the records of S like so. And we do this for every record in R. We scan through the records of S repeatedly, once per record of R. So what about the cost of this whole traversal of the joint space? Well, it is going to be based on the sizes of the tables as indicated here. So the cost is going to be to scan R once, so that's going to be the brackets of R, plus for each tuple of R, and that's the vertical bars around R, we scan all of S, so it's bracket R plus vertical bars R times bracket S, or 5,000,000,000 for this example is the cost of doing this join. Now you can imagine changing the join order, where we say instead of each record little s in S, and for each record little r in R. Now we will traverse the joint space vertically like this, as shown with the orange arrows. We cover every point in this space again, but the cost is different. In particular, we scan S once, and for each record of S, we scan R. So that's going to be 500 plus 40,000 times 1,000, which is going to be 40,500,000. This is quite a bit cheaper than doing it in the other order. So, lesson: pay attention to join orders, as they matter quite a lot. In fact, we will see this in all of our join algorithms. This is the first most simple example where we can do quite a bit better than the simple nested loops join by paying attention to I/O. So let's do that here. We are going to have a paginated, page-oriented nested loops join, where we will have a quadruply nested loop. The outer two loops are pages of R and S, and then the inner two loops represent joining tuples upon pairs of pages. So let's see how that works. We are going to take a page from R, and then for each page of R, we are going to go through the pages of S. And in the third nested loops here, now that we have gotten for each R tuple in the R page, we're going to loop through the S tuples in the S page like this. There, we will check and see if the join condition theta holds on the pair, and we will add the pair to the results buffer if so. We will do this for every page of S, for the first page of R, so in essence, we will scan through the Cartesian space one page of R at a time, instead of one tuple of R at a time, and it looks more like this. So, what is the cost here? Well, we are still going to scan R, so that's the bracket of R, but now we are only going to scan S as many times as we have pages of R. So the parenthesized expression here is bracket r times bracket s. Recall the last time it was vertical bars s times r bracket. This is going to give us a cost of only 501,000 IOs, which is significant savings over what we saw before because we were doing this at one page at a time. Can we improve upon this? Well, now you can imagine if we can do things a page at a time, we can also do things a memory chunk at a time. There's an algorithm for that actually. It's called the block nested loops join, but we will call it chunk nested loops join because the word block we said before is a synonym for page block or page. So even though in literature they often call it the block nested loops join, we will call it chunk because a chunk you can think of as many pages or blocks together. We will actually have b-2 pages to work with here. Why? Because we need one page for loading in the tuples from S and one page to store the output. So we are going to take b-2 pages of R, we'll call that a chunk. For each of our chunk of b-2 pages of R, we are going to scan through S. For each of our chunk of b-2 pages, and for each S page, we will form all matching tuples in memory. In this example, our chunk is of size 2 pages as indicated by this big fat red arrow. So it's pretty small. Then for each page of S, we form the pairs in memory and check the predicates to see if they match. In essence, we are traversing the plan space now one chunk at a time across S, instead of one page at a time across S. So what about the cost? Well, now the cost is bracket R to scan R as before, plus the ceiling of bracket R divided by b-2, which is the number of these fat arrows, otherwise known as the number of chunk partitions of R, times bracket S, which in this case is 1000 plus 1000 over b-2 ceiling times 500. If you imagine b is something like 102, which is a modest number, then we get 100 times improvement over what we had done before, for a total of only 6,000 IOs. This is quite a bit better than the billions of IOs we were doing with our simple nested loops join. You should think about this chunk nested loops join as being your default way to do nested loops join. We can obviously turn B down if we don't have a lot of memory available, or we can dial B all the way up if we have lots of memory, and we can save quite a few IOs. So chunk nested loops join is actually a very viable algorithm, particularly when we don't have an equality predicate, and where we have to actually compare all pairs of tuples.